Okay, hello everyone in a new video. So we have reached part 3 of chapter 8, which is the chapter of mechanical actions and the third unit of mechanics. And eventually we have reached section number 10. And in this section we are going to discuss the following curve. So this reminds us in the curve of the characteristic current voltage in the case of resistance. So here previously this for a resistor has been labeled by the current I, and this has been labeled by the voltage U, and in that case the name of this graph is given by the characteristic current voltage curve. So for this reason the title of this section will be the characteristic mass weight curve of G, in which G represents the gravitational field strength. Now in that section we have discussed 5 important things. Now in order to reduce the ideas, I will discuss only 4 important things. Although that we can discuss the 5th idea that is missing here, but it's okay. Then let me say that we have 4 important things to notice. And let me start by idea number 1. So we need to refer to the shape of the curve. So notice that in this case, this curve is a straight line passing through the origin. Then let me say the characteristic mass weight curve of the gravitational field strength is a straight line passing through the origin. And because we have identified the shape of the curve, then the slope of this curve will refer to the value of a G, because notice that previously this has been identified by I and this identified by U. So according to the formula, U is equal to R multiplied by I. So the missing quantity, which is R, then R represents the slope. So in this case, if we are talking about W is equal to M multiplied by G, and the x-axis is labeled by M, the y-axis is labeled by W, so the missing quantity is G, then in this case the G represents the slope. Then let me write down the gravitational field strength G is equal to the slope of the characteristic mass weight curve. Now the third idea that I want to discuss. Now this curve gives us a relation between the values of W and G. So if you know the value of W graphically, we can determine the value of M, not G. And if you know the value of M by referring to the curve, it corresponds to this point on the curve having the following value of W. So it's simply the connection between W and M. Then let me say graphically, if the weight of the object is 6 newtons. So if we know the value of g, we can use the formula to determine the mass. But now we can directly determine the value of m, because 6 newtons corresponds to this point on the curve having the value of m is equal to 600 grams. Then the mass is 600 grams. Now the fourth idea that we also can discuss is that also graphically, instead now being given the value of W, we can have the value of M. For example, if M is given by 200 grams, referring to the curve, one can determine the value of W, which is given by 2. So if the mass of the object is 200 grams, then the weight is 2 newtons. Now it's left to discuss how one can determine the slope. So now we need to answer the following question: how to determine the slope. So as usual, we all start by writing the definition. So step number 1 is to write the definition. And previously, in the case where this is given by I and this is given by U, the definition was given by the slope, the resistance of the resistor is equal to the slope of the characteristic current voltage curve. Now in this case, we are interested in determining the gravitational field strength, which is a G. So the definition will be given by then the gravitational field strength is equal to the slope of the characteristic. Instead of saying current voltage, we will say mass weight curve. So let me say the gravitational field strength G is equal to the slope of the characteristic. So I repeat, instead of saying current voltage curve, we will say mass weight curve. So the slope of the characteristic mass weight curve. Now the next step, which is step number 2, is to choose 2 points belonging to the curve, and choose any 2 points on the curve. So in this case, my choice will be any 2 points, but I will choose this point, the point A and the point B. So now I will write the coordinates of the point A and B. So as we have done in the case of the resistance, so we will start by the current and by the voltage. So the point A has the following coordinates: 200 grams and 2 newtons. And as for the point B, we have it's given by 400 grams and 4 newtons. Now step number 3, change the units of the chosen points to the SI. So in this case, this is in the SI, but we need to convert the grams to the SI because the SI unit of mass is kilograms. Then in order to convert from grams to kilograms, we need to divide by 1000. Then 200 divided by 1000 is given by 0.2. And 400 divided by 1000 is given by 0.4. And now we are ready to calculate the slope, which represents the gravitational field strength according to the following formula. Calculate the gravitational field strength using the formula. And here, as we have discussed previously, if we start with the point A in the numerator, we need to start with the point A in the numerator. And because we have ended in B in the numerator, then we must end with B in the numerator. So independent whether we start with A or B, but we need to respect the order. And now in this case, we can calculate the value of G. So here, if we are performing this experiment on the surface of Earth, so we expect that the value of G must be given by 10 newtons per kilogram. So let's calculate the value of G. Then the weight of the point A is given by 2. So let me first write the definition. So the weight of the point A is given by 2 minus the weight of the point B, which is given by 4, over the mass of the point A, which is given by 0.2, minus the mass of the point B, which is given by 0.4. Here in this case, you want to consider this expression in the numerator and this expression in the denominator. And after you finish the calculation, you need to reduce the following fraction, or you can simply plug this expression on the calculator and the value of G will be given by 10. Since everything W and M are expressed in the SI, so the value of 10 here will be expressed in the SI, which is given by newtons per kilogram. So indeed, the value of G is given by 10 newtons per kilogram. And now as a direct application, let me solve the following exercise. So section 20, exercise 10, they are telling us each of the documents 1 and 2 and 3 represent a characteristic mass weight curve corresponding to the gravitational field strength G1, G2, and G3 of 3 different planets. So this is characterized by G1, this is by G2, and this is by G3. Determine graphically G1, G2, and G3, and this can be done using the slope method. Then let's start by the first document. So as usual, we need to follow different steps. We will start by writing the definition. The gravitational field strength is equal to the characteristic. So I will always refer to electricity. Instead of saying current voltage, we'll say mass weight is equal to the slope of the characteristic mass weight curve. Now the next step is to choose any 2 points. Let me choose this point and this point, say for example. Then the coordinates of the points A and B are given by, we always start by the mass then the current. So 10 kilograms with 16 newtons. As for the point B, here we have 30 kilograms with 48 newtons. Now we need to make sure that all of the given units are in the SI, and indeed all of the given units are in the SI. Mass is in kilogram and weight is in newtons. So now we directly move to the last step, which is calculating the value of a g. Now here we are talking about document 1, so it's given by g1, which is given by wa minus wb divided by ma minus mb. Now the value of wa is given by 16, the value of wb is given by 48, over, now the mass of a is given by 10, and the mass of b is given by 30. And here, as I have mentioned previously, that we are calculating a fraction consisting of a numerator and a denominator. Both require calculation, or you can simply plug it on the calculator. And by doing so, the value of g1 is given by 1.6. Since everything is expressed in the SI, so the value of g1 will be in the SI, which is newtons per kilogram. So the value of a g1 is given by 1.6 newtons per kilogram. What does this mean? Each kilogram on this planet, it's being acted by 1.6 newtons. Now let's refer to the second document, which is document 2. Now also we need to determine the gravitational field strength corresponding for this document or for this curve. And we need to follow the same procedure. We always start by writing the definition, which is this. So the gravitational field strength is equal to the slope of the characteristic mass weight curve and now we need to choose 2 points. So let me in this case choose, this is the point C and this is the point D. Just prove that the positions of the points are independent, choice independent. Now the coordinates of the point C are given by, so it's given by 1000 grams and 10 newtons. As for the point B, it's given by 1500 grams and 15 newtons. Now the next step is to convert these units to the SI. So notice that the mass is in grams, and we know that the SI unit of mass is kilograms. So 1000 divided by 1000 is given by 1 kilograms, 10 newtons. So notice that here from the early reading, each kilogram is being acted by 10 newtons, which means that we are on the surface on the Earth. And as for the point D, dividing it by 1000, it's given by 1.5 kilograms, 15 newtons. Now we are ready to calculate the value of G1, G2, referring for document 2. So G2 will be given by the weight of the first point minus the weight of the second point, independent whether we start by C or D, but for the denominator we need to respect the order that we have started with. So MC minus MD. So the weight of the points is given by 10 minus the weight of the point D, which is given by 15, divided by MC, which is given by 1, minus 1.5. Considering the previous notes and plugging this on the calculator, then the value of G2 is given by 10. Since everything is expressed in the SI, so the value of G2 will be in the SI, which is in newtons per kilogram. So the value of G2 is given by 10 newtons per kilogram. And finally, for the last document, document 3, let me start by writing the definition. Is equal to the slope of the characteristic mass weight curve and by this let me choose 2 points on the graph. So Let me choose that this is the point E and this is the point F, say for example. Now the coordinates of E and F are given by, so E for kilograms corresponding for 100 newtons. And as for the point F, we have 5 kilograms corresponding to 125 newtons. So now we are done with step number 2, and the same for step number 3 because all of them are in the SI. Now we are directly ready to calculate the value of G3, which is given by the weight of the point E minus the weight of the point F divided by the mass of the point E minus the mass of the point F. So the weight of the point E is given by 100 minus that of F over the mass of E, which is 4, minus the mass of F, which is given by 5. Plugging this on the calculator, then the value is given by, so here what do we have? Here we have 25 over 1, so it's 25 newtons per kilogram. So G3 is given by 25 newtons per kilogram because everything is expressed in SI. Now as for number 2 of this exercise, they are telling us identify the above planets, and here the given is given. So the given, we have the gravitational field strength on the Moon, on Mars, on Earth, and on Jupiter. So as for document 1, we have that the value of G1 is equal to 1.6. So G1 is equal to the gravitational field strength of that of the Moon. So it's given by 1.6 newtons per kilogram. In this case, the Moon, or document 1, corresponds to that of the Moon. Now as for document 2, we have that the gravitational field strength G2 is equal to that of Earth, which is equal to 10 newtons per kilogram. For this reason, Earth corresponds to document 2, or it's more convenient to say that document 2 corresponds to Earth. Now finally, as for document 3, its value is given by 25, corresponding for Jupiter. So the value of G3, which is equal to G of Jupiter, which is equal to 25 newtons per kilogram. In this case, Jupiter corresponds for document 3. So this is it for this exercise. Let me move on. And now we have reached section number 21, which is the weight. Now previously we have discussed the weight as the magnitude. Now we need to discuss the weight as a force, and we will discuss the physical definition and the mathematical definition as well, as we have mentioned in the beginning of this chapter. So let me start by the physical definition. So by the physical definition, we mean the action exerted by whom on whom, and in this case we can say that it is the force exerted by Earth on another object. This force is called the force of gravity of the Earth. Or let me say, okay, the force of gravity of the Earth, Now here, for sure, whenever we say the weight, we are discussing the weight of the Earth. We know that there is the weight on the Moon, there is the weight on Jupiter, but most of the cases, whenever we are discussing the weight, By that we mean the weight on Earth, and we cannot know until the value of g is being specified. Whenever the value of g is given by 10 newtons per kilogram, it means that we are performing that experiment on the surface of the Earth. So this is the physical definition of the weight. Now let me refer to the mathematical one, which is given by characteristics of the weight as a vector. So here we are discussing the pilldom, and they must be listed in this order. Let me start by the point of application. The line of action, the direction, and finally the magnitude. Now what is interesting about the weight is that always the first three properties are always fixed, and they are given by the center of gravity g. The line of action would be always vertical, independent of the scene, and the direction is downward. Now as for the magnitude, here we can open the following discussion. The magnitude of the weight can be determined using several methods or different methods. The magnitude of the weight is calculated using one of the following methods, one or more. So let me start by discussing the first one that we have seen previously, which is given by the weight is equal to m multiplied by g. Then we are all familiar, I expect, with this one. Now the second one that we have also faced, which is given by using a spring balance or a dynamometer. Now the third method is graphically that we have now already discussed. And the third one, that the final one that we will discuss in the coming chapter, which is given by the condition of equilibrium, or let me say using the vector relation at equilibrium. So as we shall see in the next chapter. Then I'm not asking you to memorize the following, the different methods that I have listed now. Now, just I have listed them to mention that one can determine the weight in different method. So don't restrict yourself in memorizing this or think about this or this. So it depends on the problem itself. And now let me solve the following exercise as a direct application also. So given an object A of mass m is equal to 3 kilograms, g is the center of gravity of A. List all the properties of the weight, specify the type of the weight. Then let me start by the properties of W. So weight W. Then in this case, the point of application the line of action and the direction. So always the three properties of the weight are always fixed, and this is given by the center of gravity g. the line of action would be always vertical, the direction is downward. And now the magnitude in this case, because we have the mass, so let me here add also as a given take G is equal to 10 newtons per kilogram. So now I have specified that we are performing this experiment on the surface on the Earth. So because the mass and the value of G are given, now the magnitude of the weight depends on the object itself as well as the planet, which means the two bodies that are at interaction, and this is the physical definition of the weight. So W is equal to M multiplied by G, so we don't forget to write the formula because this is usually give it half a mark. Then 3 multiplied by 10, everything is in the SI, which is given by 30 newtons. So in this case, the force of interaction between the weight and the Earth, it is worth 30 newtons, and it's being applied at a point G vertically downward. So it's always good or convenient to give the force the following description by the force exerted by a body on another, and list also or to discuss or to mention the mathematical properties. Now finally they are telling us to specify the type of the weight, and here they are talking about whether it's a contact force or acting at a distance. So we always know that the only three forces that act at a distance are given by the weight, the electric, and the magnetic, and all other forces are classified as contact forces. And here, with no exception, the weight W is classified as action at a distance or acting at a distance. So whenever they ask us about the type, the classification, we need to mention whether it's acting at a distance or a contact force. And now let me move to the next section, which is the normal reaction. Now section 23, the normal reaction. Now let me write the physical definition. So, and let me say any object placed on a support and here by the support it means that it may be a table, a floor, or a ground, so or even an inclined plane. So anything that is preventing a solid S from falling down, which by this it is giving a support, is subjected to a force preventing it from falling down. Okay, this force, so this is, first of all, this is the physical definition. It is the force exerted by support on a solid S. So this force is called normal reaction, or even this is known as the reaction at the support. Now let me here illustrate. Suppose here we have a table or a ground, and we have a solid S resting on the ground. So the first thing that you should think about, because the solid have a mass, it will be directly subjected to the weight, which is vertically downward. So because the weight is acting on the solid, we expect that the solid must fall down. In order to explain why the solid S is not falling down, this is because the ground is preventing it from falling down, but we need to explain this at the level of the forces. Then we will introduce a new force, which is called the normal reaction. So the normal reaction is not weight, nor electric, nor magnetic, so it's a contact force. Then it will be completely opposite to the weight because it needs to balance the effect of the weight, so it will be something like this. Okay, so the thing is that whenever we have a support we will have a normal reaction. Now let me write the characteristics of the normal reaction. And let me start by the first one, which is the point of application. So because the normal reaction is classified as a contact force, then the point of application will be the point of contact. Between the two bodies that are at interaction, in this case between the object and the support. Now as for idea number 2, which is the line of action, so it will be always perpendicular to the support. Now during the problem we will specify whether it's vertical, horizontal or oblique, but the thing that is fixed is it is perpendicular to the support. Now as for idea number 3, which is the direction, the direction may be upward, downward, so let me say upward to the left, to the right, or even right, etc. And this depends on the problem itself. So whenever we are able to specify the point of application and specify the line of action as well, one can directly specify the direction. As for the magnitude, so the magnitude in this case can be determined from the vector relation. Let me say the following: the magnitude of the normal reaction is calculated from the vector relation at and this will be discussed in the coming chapter, which is chapter number 9. And now let me consider the following example on a solid S subjected, or an object M subjected to two forces. So let me illustrate that this is an example. So what's happening here in this example? We have an object M rests on a table. So G represents the center of gravity of the object M, and A is the point of contact. So G is the center of gravity of the object M, and A is the point of contact between the object M and the support. So here, because the solid has a mass, because it has a center of gravity, then it will be directly subjected to the weight, and because there is a support, there is something in contact with the object, so directly there is a normal reaction. Then let me write down that G is the center of a gravity of M, and A is the point of contact between the object M and the support. And let me here say the forces acting on M in this case are its weight, W vector, and in this case the normal reaction. So always think whenever the object has a mass, then it will be directly subjected to the weight. Whenever there is a support, then it will be directly subjected to the normal reaction. And now let's complete the following table. So we need to list the properties of these forces. Let's start by the weight. So how can we represent the normal reaction in this case? Because the weight is always vertically downward, then N must balance the effect of W, so it will be like this. Moreover, notice that it is represented at the point A, perpendicular to the support, away from the object, or opposing the action of W. So the weight will be the center of gravity of M, which is G. So the center of gravity G. The line of action is always vertical, and the direction is downward. Now, as for the normal reaction, the point of application, it will be the point of contact between the support and the object, which is A. Then let me say point of contact. Between the object and the support, which is A. So this is the important one. It is also a good habit to write this statement. Now in this case, the direction, we always know that the line of action is perpendicular to the support. And in this case, perpendicular to the support, it is upward. Sorry, it is vertical, because we are discussing the line of action. And in the direction, in this case, it is upward. So this is it for the reaction at the support. We should always think about this the reaction at the support, or the normal reaction. It is the force preventing a solid S or M from falling down. And now let me move to the other section, which is section number 24. And the title of this section is the tension. Then let me give the physical definition of the tension before discussing the mathematical one. And let me say any object suspended from a string or even a spring, as we shall see in the coming chapter, is subjected to a force preventing it from falling down. Then here what we are doing is exactly the same discussion that we have done in order to introduce the normal reaction, then preventing it from falling down. The force is called the tension force. So in order to illustrate what do I mean by this statement, suppose here we have a string. From one end it's fixed to a support, and from the other end we suspend a solid S. We know that because this solid have a mass, it will be directly subjected to the weight, which is applying an action vertically downward like this. Now we need to explain why the solid S is not falling, because due to this string, and we need to explain this at the level of the forces. Then we will introduce a tension applied at the point A, say for example here, opposing the action of the weight. So one should always think whenever we have the string, whenever we have a string, then it will be directly subjected to the tension force. Now what about the classification of the tension force? Simply because it's not electric nor magnetic nor weight, then it is classified as a contact force. So then here let me specify the characteristics of the tension. So recall that the tension is classified as a contact force. Let me start by the first idea, which is the point of application. Now, because it's classified as a contact force, then the point of application will be simply the point of contact between the two bodies that are at interaction, and they are given by the string and the object which is suspended from the spring. So a string. So the point of contact between the object and the string. Now, as for idea number 2, we need to discuss the line of action moving in the order of the Pilgrim. So we cannot specify the line of action, the tension, unless we have a scene, but what we can say is that it is along the string. So the direction or the line of action of the string specify the line of action of the tension. Now idea number 3 is the direction, and this it will be opposing the action of other forces or away from the object. So it may be upward to the right, or even right, or etc., and this depends on the scene itself. As for number 4, the magnitude. Now exactly similar to the case of the normal, the magnitude in this case undefined, in a sense that it is not determined by a certain formula. Here we are discussing the tension in a string. For sure in a spring it will be it will obey Ohm's law, sorry, not Ohm's law, Hooke's law, because they are exactly the same. Now let me say for the magnitude that the magnitude of the tension is calculated via several methods. As we shall see later. So one of the methods, it will be Hooke's law to determine the tension in a spring, not a string, and the condition of equilibrium, which is the vector relation. And now let me give the following example. And let me say that here we have a solid S connected to a spring. Because the solid has a mass, then it will be directly subjected to the weight. What is preventing the weight from falling down is the tension T in the string, and this is straightforward because whenever we have a string, we have a tension. So an object suspended from a string the end of the string is fixed to a support. So one end of the string is fixed to the support while the other end is fixed to the object. Let me say here that G is the center of gravity. of M, and B is the point of contact. Between the object and the string. So B is the point of contact between the solid and the string, so both objects are connected at the point B. Then let me say the forces acting on the object are its weight and the tension. And in this case, the weight and the tension are represented in the following diagram. Then let's complete this table. So always the first three properties of the weight are fixed and they are seen independent. So let me say center of gravity G. As for the line of action, it is vertical. And as for the direction, it is downward. And recall that these three properties are always fixed and seen independent. Now the tension, as for these properties, they are determined by the line of action and the line of action of the string. So now because the tension, it's not the weight nor electric nor magnetic, so it's classified as contact force, then the point of application will be the point of contact between the two bodies that are at interaction and given by the string and the solid S. So let me say here the point of contact between the object and the string, and here it's extremely important to mention what's the name of this point, which is B. Now as for the line of action, what we know is that always it's given by along the string, and in this case along the string is vertical. Now as for the direction, it opposes the action of other forces, or it's away from the object. In this case it is upward. So this is it for the tension, and that's it for me in this video, guys. In the next part we are going to introduce the electric force and the magnetic force and solve exercises on this chapter.